we'll define a term which is called reuse distance. So the reuse distance is the number of accesses seen by a cache set between two accesses to the same cache line. So for example, here, if we have this access stream coming to a particular cache set, so between two accesses to Q, we have 6 distinct accesses: T, S, W, Z, Y. Then S has already come, T has come, W has come, and then V. So 1, 2, 3, 4, 5, 6. T, S, W, Z, Y, V. So 6 distinct accesses have come. That means reuse distance of Q is 6. So if reuse distance is greater than the associativity of the cache, that means the number of bays in the cache, then second access to the cache line will not lead to a cache hit. So this out, of course, if you don't understand it, is fine. If you understand it, is fine. So reuse distance, it just shows that after how much time will I reuse it. For example, you study a computer architecture, suppose this semester, and then you start reading it after probably 4 years, right? Because probably when you are working in a job, you require computer architecture knowledge, so you pick up the book. You find out that, oh my God, because it was so old and I had to read so many books in between, that I evicted that book from my bookshelf. So if between these 4 years, if you had to read so many other books, then it is highly likely that you throw away this book. But if during these 4 years you did not read any other books, you probably did not need it, then your bookshelf, if at all you purchase this book, this book will remain in your bookshelf. So that's the idea, reuse this. That means after how much time will you reuse this item? Okay, so this is the matrix multiplication code. This is, of course, before blocking. So here, remember, we are multiplying two matrices, both of which are 2D matrices, n cross n. Okay, we are multiplying two matrices. So for multiplying two matrices, we have 3 levels of nested loop. It is not 2 levels. Sometimes, I ask students, especially during interview, do you know how to write a matrix multiplication code? They don't know. So this is a very, very basic code actually. So we take this I goes from 0 to n, then j goes from 0 to n, 0 to n minus 1, and this r is just a temporary variable. We store I k and z k z, and we multiply it, and we keep on adding it. Once the product is ready, we transfer it to the x. So x is the output matrix, and y and z, they are the input matrices, and x is initialized to 0. So now we assume that the cache is fully associative, so there is no conflict miss. Okay, so if you don't know conflict miss, it is fine. So now let us see how many accesses are there in this code. Suppose n equals to 6. So we are accessing y and z. So that means this is one access, this is one access. So 2 access in this for loop, and because n is 6, and of course one access here, right here. So n equals to 6. So 6 into 2, right? 6 into 2 plus 1 for this x. This is 6 into 2 plus 1 multiplied by 6 and 6. So that is 468 accesses. Now, suppose even if you assume your cache has infinite capacity, but first time
Sir, will you say it again? Sir, will you say it again, sir? How 468 access?
468. See, you just count how many times we are accessing. So suppose y is 1 here, right?
Yes, sir.
So see, first of all, you ignore the accesses to r, and these are k, I, j, k. So that you don't count. Just count how many memory accesses you have to make. So every time you access x, either read or write x, y, or z, you have to make one memory access, assume.
Yes, sir.
So here you have to access y, right?
Yes, sir. One.
Here you have to access z.
Yes, sir.
So one access for y and one access for z. Okay?
Yes, sir.
Then you multiply it with n, because this for loop will go from 0 to n minus 1.
Yes, sir.
So how many times? N.
It's 10. Sorry. N. N.
So N is 6, right? So that means 6 times.
Yes, sir.
So 6 times this. So 6 into 2
Yes, sir.
plus X here, 1.
Yes, sir.
This is 6 into 2 plus 1.
Yes, sir. Yes, sir.
And
I
then
got it.
this is 6 times, this 6 times.
Yes, sir. Thank you.
So yeah. So now each of these matrices are 6 cross 6, right? X is a 6 cross 6 matrix. Similarly, Y is a 6 cross 6 matrix. Z is a 6 cross 6 matrix. Okay, so every time when you access one element of X, Y, or Z, you will enter one miss. At least minimally. That is a minimum. There is a minimum number of misses you will have. So if you don't know compulsory miss, ignore this fact. So minimum number of misses you will have is 108 because you have 3 arrays X, Y, and Z. Each array has 36 elements. So minimum misses you will have is 108. You can't go below it. You can't have less than 108 misses. Is that fine? Okay. So this is the snapshot of the arrays when n equals to 6 and I equals to 1. So here remember this is the X matrix, which is the output matrix. Now this is the Y matrix and this is the Z matrix. So what we are doing is we are taking one row of Y and one column of Z. Similarly, one row of Y, then one column of Z, one column of Z, one column of Z, one. Similarly, so this was done. Now we came to the second row of Y. We come to second row of Y. Then we take one column, one column, one column. Then we are taking 1, 1, 1. So just now, that means very recently we have accessed these 3 columns. And of course, we are accessing one row of Y. That's how the matrix multiplication operation works. And by multiplying it, we generated these 3 elements of X. That means by multiplying this row with this column, I generated this. By multiplying this row with this column, I generated this. And by multiplying this row with this column, I generated this. Okay, is that fine? Okay. Now, one more thing you can observe is, see, for X, we have written I and J. Okay, so why? Because for X has I and J. Y has I and K. Right? So Y has I and K. And Z has K and J. Right? Z has K and J. K and J. Okay, these are the indices which we are using to access a particular array. So here in this figure, age of accesses to the array elements is indicated by the shade. White means we have not yet accessed those elements because till now I has just reached 1. So I, as you can see, I is here, this is I, and this is I. So I have just reached 1. That means we are still at row number 1. We are still at row number 1. That means we have not touched row number 2, 3, 4, 5. Light means older accesses because long ago we finished this, and dark means very recent accesses. So just now we finished accessing this, and these 3 elements. So what we are doing is we are repeatedly reading the elements of Y and Z to calculate new elements of X. So the variables I, J, and K are shown along the rows and columns to access the array. So that point is fine. So as I already showed, even for matrix transpose, that storing the arrays in row major order or column major order will not solve the problem because both rows and columns are used in every loop iteration. Right? For Y, we are accessing row wise, and for Z, we are accessing column wise. Okay, we are accessing row wise for Y and column wise for Z. So that's why we can't just either do loop interchange, or we can't see if we were able to solve, if we were able to store y in row major order and z in column major order, that solves the problem, but that's not possible usually. Okay, so and if you want to store both of them in row major order or both of them in column major order, that also does not solve the problem. We have already shown that for matrix transpose. So till this point, we have just shown that conventional solutions will not work. That means all the solutions that we knew before cache blocking, they will not work. So is it fine? Is it clear to everyone? Any questions till this point? Okay. Now, this is again, we have written the same code that we had written previously. There's nothing new here. Now let us try to observe what we are doing. Now we focus on these, this part of the code. You don't focus on all the code. Just focus on these inner two loops. So within these two inner loops, what we are doing, we are reading n by n elements of z, because see, z has k and j, and k is here and j is here. So within this loop, k and j will change from 0 to 5, 0 to 5. That means we have read the entire z once. Okay. Now, for y has I and k. I does not change within these two for loops. I does not change. Only k changes. Okay, so that's why we are reading the same n elements in a row of y repeatedly. All right, we are repeating the same n. So that's what was shown here. We are reading the same n elements. These are the 6 elements of y we are reading repeatedly. For every column of z, we are reading these elements of y. So that means this one row of y we are reading repeatedly. And I again does not change. So we will only j changes from 0 to 5. That means we will write one whole row of x. Like that's what is shown here. We will write this whole row of x inside this and inside the two for loops. That means this inside this for loop we are writing every time we are writing one row of x. We are reading one row of y and we are reading the whole of z. These are all the accesses which are happening. So, okay, I think you ignore the fact number of capacity misses. There are 3 types of misses: compulsory, capacity, and conflict. So we have already shown that conflict miss cannot happen here because our cache is fully associated, and this compulsory misses will always happen. So we just have now capacity misses. So again, you just ignore the fact. This point you can ignore for now. Now, the number of misses depends on n and the size of the cache. If your cache size is infinite, suppose the cache size is very, very high, then you will just have these number of misses, 108 misses. Right? If you have cache size very, very high. But if your cache size is not very high, so that's what we are saying. If it can hold all the 3 n by n matrices, then everything is fine. We'll just have compulsory misses. That means only when we access the element first time, that time we will have the misses. Okay. If the cache can hold only one matrix, suppose Z matrix, and one row of n, suppose this Y, then at least the ith row of Y and the array Z may stay in the cache. So that's what we are saying. If we can at least hold Z and Y, we can hold that. That means I will show you the number of cache misses for different size of the cache. Then you will appreciate this point. That means as we grow the size, that suppose initially my cache size is 0. After that, I try to see that for each cache size, how many cache misses I see. Number of cache misses will slowly reduce. But the lowest I can get is 108. I cannot go below it. So cache blocking, I have already explained what is the key idea. So whole point is that divide and conquer, which one of the students very nicely said, Anupam. So we divide the working set so that each piece fits in the cache. The goal is to maximize access to the data loaded into the cache before the data are replaced. So here is the code after blocking. We have not blocked this for loop. This for loop is unchanged. We just blocked two for loops, the J and K. Two for loops, we block them. The blocking factor is B. Okay, so small j equals to jj, where jj is 0 to n, and then it doesn't increment by 1. Jj does not increment by 1, but jj increments by capital B. Okay, so now you can see within this for loop, we are not going all the way till the end of the for loop. We are just going from jj to jj plus b. That means only only b. That means a block size number of rows and a block size number of columns here. K is, we are not going k from 0 to n. K is just going from kk to kk plus b. That means the b size row and b size column. That means a B cross B tile. We are only operating on B cross B tile. That's what I showed through the figures in the transpose, the last presentation. Instead of going all the way on the entire matrix at a time, we are working on sub-matrix, which has a row size of capital B and column size of capital B. So two inner loops now computing steps of size capital B rather than full length of X and Z. B is called blocking factor. So we are operating on sub-matrix, or a block or a tile. It's called a tile or submatrix of size B by B. So this is the code. So this, how do we do the tiling? You have to memorize. Please memorize that. If you can understand, you can write it naturally. If you can't understand, please at least memorize it. So here, as you can see now, previously we were working on the entire Z matrix. Now we are working on a suppose B equals to capital 3, so we are working on 3 cross 3. Okay, so compared to the original code, less elements are accessed because each time we are working on a small submatrix. Now the reuse distance of elements is reduced, so cache misses are reduced. So reuse distance just means after how much time did I reuse the same element. So previously I reused after a lot of distance. Like here, although I'm repeatedly reading Z, but in this case, I first go through the entire this column, this column, this column, this column, this column, this column, and then I come back to this Z. That means after 36 elements of access, at least after 35 other elements of Z, now I'm again referencing the same element of Z. Whereas here, after this, I'm again coming back here. This is just 9 elements. That means after only 8 elements, I'm again accessing the same element. Whereas in the previous case, after accessing 35 elements, I access the same element again. And I hope you agree now that reuse distance of Z is reduced. Same for Y. Okay. So we are accessing the same element of Z after, with a lower reuse distance. So I can show you the code. I will show you that also. But here is the result of that code. So with different cache sizes, what is the number of cache misses? So this is without blocking. If you don't do blocking, then with cache size of 16, I get 237 misses. Whereas in the blocked code, I get only 168 misses. Finally, at least first show this part. When the cache size is sufficiently large, right? 36 plus 6 plus 6, almost there, right? That is 48. So around 48 or something, we get the minimum number of misses. We can't go below it. Even if you increase it after 48, it will not go beyond 48. That means the lowest number of misses we get is at around 108. So, but initially the number of misses in the without blocking is much higher than that of with blocking. And as we increase the cache size, number of misses are reducing. Here now in the blocking, they are also reducing, but at the slightly slower rate. And at the cache size of 48, we get the minimum number of misses. Whereas here, without blocking, even before we can get it around same number of misses, 100, 108 and 112, which is not much different. So now I will show you this code actually from where I got this data. And let me see. Yes, that code just. Okay, this is for optimal. Can I do it for LRU? Just I'll show you the code if you are. Doesn't. Okay, my screen. So I hope you can see my screen. So I have this access sequence to a cache without blocking and access sequence with blocking. Here's that. Access sequence without blocking. Yeah, this is the access sequence with blocking. Without. Yeah, here. These two are the. I've just dumped. Yeah. Here you can see. If you do blocking, then what are the elements of y, z, and x that are accessed? So here for computing this element of x, I initially just call y00, z00, y01, z10, y02, z20, and then I save that result in x00. And x00 is updated in two steps. First, it is updated here, then it is updated here. Whereas here, x00 is updated only once, right? As you can understand, because here there were total of 1, 2, 4, 6, 8, 10, 12. So x0 is updated after 12 elements, and here it is still updated after 12, but we compute 6 here and 6 here. We don't compute everything which is required to get x in a single step. First we get 6 elements, and then we get 6 elements, and then we store it in x. So this is the access sequence which I have, and I also have a cache emulation binary which feeds this data to a cache using optimal replacement policy. So using optimal replacement policy. So and then it prints the number of cache misses. Okay. So cache size is given here in counters 2, 4, 6, 8 up to 50. So I print all that. This is without blocking how many misses are happening. So for example, at a cache size of very small, 378. Here When the cache is so small, it doesn't matter whether it is blocked or unblocked. So, however, if you see probably starting from here, cache size equals to 14, there's a lot of difference. And as we come down at cache size of 50, they have, even at the cache size of 48, they have similar number of misses. So this is, and actually in cache, in the matrix transpose, which I discussed yesterday, I showed you the diagram of the whole cache. What is the cache block which is stored there? If you want to do that analysis, you are welcome to do it. I did not do it. I just have shown you this emulation binary, which has done that for me. Okay. So, and any questions? If you could not understand it, please go through the code again and try to solve it. I will upload this. I will not give you cache emulation binary. I will just give you this access sequence and this. Maybe I can give you just the binary without the source code, and you can run it with this script if you want to run it and then see how many number of misses happen with block code and without block code. And if you want, actually, you can just put a printout statement. For example, here you can put a printout statement, so here first y is accessed, then z is accessed, then x is accessed. So you can put a printout statements here, and that's how I got this access sequence. I put a printout sequence. Okay, first y access, then z, then again y, then z, y, then z, finally x. That's what is happening here. So this is how I have got this access sequence. Okay. Any questions you have? Please ask. This will become clear only when you go through the slide yourself. Okay, if you have no question, I will go forward. Now we'll see tiling of yes.
Sir, how to calculate compulsory mix when in the case of multiplication, normal multiplication, matrix multiplication?
Compulsory mix just means what is the misses that will compulsorily happen. Okay, so when you fetch the data for first time, definitely it will lead to a miss because this is just the first access to that element. Okay, so here, how many distinct elements we are accessing? We are accessing total of 108 distinct elements because we are accessing 3 arrays, x, y, and z. X has 36 elements, y has 36, z has 36. So 3 into 36 is 108. That is the compulsory misses.
Reason.
Okay. I'll go forward if you don't have any question. So now we'll discuss tiling of convolution kernel. We just now discussed tiling of matrix multiplication. So this is now these are the original, this is the 6 levels of nested loop for convolution. Usually what happens, this value of capital K, this one is very, very small, like 3. So our kernel is 3 cross 3 kernel, right? If you see in LXNet, we are using some of the kernels which are 3 cross 3. Some of the kernels are of course 11 cross 11, but in neural networks, many kernels are like just 3 cross 3. So this K is very, very small. So because this is already very, very small, we don't further tile it. What will you tile? It's already 3. What more will you can't make it further smaller. But usually this R, C, M, and N, they are large values. So that's why we tile them. So here this code shows that we have tiled all these for loops. So we have now, instead of these for loops, we now have this 8 for loops. And of course, these 2 for loops were already there. And corresponding to that, we have changed this row to TRR, column to TCC. The weights, these indices have changed, and this input fmax, these indices have also changed. So this is the convolution layer code after tiling. So again, to visualize it is extremely difficult. So I will not try to do that. You can just see how we have rewritten the code. At least the code part you can understand. Here we have different blocking factors. This is the TR. Previously we were using a square tile. Here we are using probably rectangular or whatever, cuboid. Maybe 4 dimensions. I don't know what is the term for that, but some it's a not it's not a square. So here the tiling factor can be different in different dimensions. So some loops are tiled, some loops are not tiled. So now there are some limitations of tiling also. So tiling helps us improve the efficiency of cache. However, it harms the efficiency of accessing the main memory. That means we are fetching the data from main memory to the cache in an order that is convenient for the cache, but that is not convenient for the main memory, because in the main memory we are no longer doing contiguous access. We are doing non-contiguous access. That you can see from this part. Like here, without blocking, you can see like Z00, then Z10, Z20, Z30, Z40, right? Whereas here now Z is accessed fine, but then I will again fetch it Z later on. Some elements I'm fetching, this we'll fetch it later on. So here, if you see from the main memory perspective, the efficiency of accessing main memory is harmed. So tiling scrambles the data access pattern of main memory, which reduces the efficiency of main memory access. So actually till now we have not discussed main memory. I will also not discuss in this course. Main memory is actually DRAM. In DRAM also, if we are accessing nearby elements, it's always very, very good, just as it is for cache. If we access the nearby elements, it's called spatial locality. That's very, very good for DRAM memory. So, so I will, maybe I'll remove this slide because we have not discussed, main memory architecture. So this will be a little difficult for you to understand. So without tiling, at least without blocking, reading data entails access to contiguous elements, which is efficient. But after tiling, you are accessing non-contiguous elements, which is very inefficient. So that's why tiling improves cache utilization efficiency, but it harms main memory efficiency.